All right, play something easy for a change. Give a Little Bit by Supertramp. Okay, so the last part of the video, what we're going to be looking at is the derivatives of the other inverse trig functions. And I'm not going to derive where these things come from and everything. I'm just really just giving you what these rules are. And we have the derivative of a inverse tangent is 1 over 1 plus x squared. The derivative of the inverse cotangent is the same thing, except it's negative. All right, and the derivative of an inverse secant is kind of a weird formula. Oh, this is 1 over absolute value of x times square root of x squared minus 1. Derivative of inverse cosecant is the same thing since it's negative. So it follows that nice pattern. If the derivative begins with c with your trig functions, you have a negative answer. So it's that same kind of pattern on that. So mainly what we're going to do is just focus on some of these derivatives, just using the rules. So we'll do some examples. A lot of chain rule will be involved in this. So what I have here is I have a function inside of a function. My big function is inverse tangent. So I'm going to utilize this formula right here. So f prime of x, just follow what the formula tells you to do. It's 1 over 1 plus the something squared. And that something is a function. So that pops in there like that. Let's write that a little bit better. Okay, so that goes in. Then don't forget we're doing the chain rule. So we got x the third in there. And then we're going to multiply by the derivative of the part inside like that. So yeah, we're working with a chain rule. So it's important to see what I'm doing with that inside part. Okay, so this will be 1 over 1 plus x to the 6th. You multiply the exponents. Just a kind of a quick reminder that's worth writing. I mean, all this problem means is this. X the third means x times x times x. X times x times x to the second means x times x times x times x times x times x. Sometimes it's worth reminding yourself of why you do what you do in math. Okay, so that's 3x squared with your derivative of x the third. Not anything you can do with the problem other than multiply the fraction straight across. And this right here would be a beautiful simplified version of that derivative. Okay, so that's pretty simple on that one. Okay, the next one, again, you got a chain rule. Your function inside is a secant. Okay, so the big function is inverse cosecant, so we're just going to follow what this tells us to do. Okay, just follow it directly. So we have f prime of x. We're going to have a negative answer because it begins with c, cosecant. Now we have absolute value of x. Now see, that thing will be replaced by the secant. Now just put an x, put what the function is. And then the same thing happens here. You'll have something squared minus 1. So what pops in there again is the function. The secant of x is going to go in there. And then we'll see, we got to use the chain rule also. Okay, and also need to multiply by the derivative of the secant x. So you've got your chain rule involved in here as well. Okay. All right, so let's go ahead and let's work this out and see how far we can take this then. Okay, what we're going to find on this absolute value, there's really nothing you can do with this, with that secant in an absolute value because the secant, you know, can be positive or negative. And so that you just have to leave that in that absolute value like that. So we're going to leave that alone. And then we'll write this under the square root as secant squared x minus 1. And there's a potential on that for using an identity, which we'll do in a minute. And then the derivative of a secant is a secant x tangent x, like that. Okay, now let me go through identities. I'll show you something that I do all the time. There's 3 Pythagorean identities. The one that I remember the best, and everybody remembers this one right here. The other ones are a little bit less or easier to forget, and I always derive them. So if I take this and divide every single thing by the cosine squared of x, let me show you what happens. Okay, if you don't know this, this is worth knowing. And a sine over cosine is a tangent. Okay, cosine over cosine is 1, and 1 over cosine is secant squared x, like that. So what we could do is we could rearrange this. If I move the 1 over here, then I get tangent squared x equals secant squared x minus 1. So notice that's what pops up right here. So we can replace that with a tangent squared, and then we can simplify that a little bit. Okay, so now we have negative 1 over absolute value of secant x, and then this will be replaced with the square root of tangent squared x, and then we have times the secant x, tangent x, like that. Now, what I'm going to do on this then is on a tangent function, what's going to happen if you square, you know, any value on a tangent, it's going to give you a positive number. So that comes out of the radical. You'll get negative 1 over absolute value of secant x times tangent x. And then we can cancel out the tangent x like this. Okay, and we'll end up getting this. Now I'm going to leave that in an absolute value. So I get negative secant x all over absolute value of secant x. And then I'll talk about how you can handle that absolute value on that in just a minute here. I'm going to put this in the graphing calculator, so I'm going to pause the video just briefly. Okay, so let me go ahead and show you how you'd finish this up. So basically, what will happen on this is this absolute value right here, you're either going to get a positive in the bottom there. So you could actually go ahead and just do a cancellation. So let me show you something. Okay, so let me explain. I'll show you something on the graphing calculator. I was had to pause to take a look at something on my calculator. So basically what would happen, you're going to get either a plus or minus 1 on this. And it's going to kind of depend on what the value of x is. I think the best way to show this is just on a graphing calculator. So we're going if we're doing y equals inverse cosecant of secant x, now TI does not have an inverse cosecant button on it. What it has, but what you can do is you're going to put it in your graphing calculator like this. So what you have to say is inverse sine of 1 over this argument right here, like that. So you have to put that in like that. And the thing is, 1 over secant is cosine, so what we put in our calculators, we put in the inverse sine of the cosine of x. So that's what I put in my calculator. I put that in, and then I just, if you graph this like in a standard window, you get this kind of back and forth between slopes of 1 and negative 1 on this that we've seen several times. So kind of hard to see on the graphing calculator on this, but I could do this and just show this to you. If I go secant, trace, option 6, and if I just do like the derivative at x equals 1, see it's given negative 1. So that slope of that tangent's negative 1. And if I continue to go through there, it's going to change. So anyway, that would be plus or minus 1 is what you would get on that. That's how you'd have to handle that. Okay, so let's go ahead and pause the video. And I want you to just work out the derivatives on number 1 and number 2. You can refer to the formulas on the previous page. So let's go ahead and pause and see how you do with these. Okay, so you can look over what my answers were, see how you did. So the first one, you could do one of two answers. You could just leave this alone, or you could FOIL that out and collect like terms. But this basic one right here, the formula for the derivative of an inverse cotangent is negative 1 over 1 plus x squared. but we have a function inside, so this is a chain rule. So I did -1 over 1 plus 2y squared minus 4 squared. Just plugging that in. Then I multiply by the derivative of the function inside. And the derivative of 2y squared minus 4 is 4y. Then I just multiplied across, and that's good enough. You got that answer. If you FOILed this out, you would get 4y to the fourth minus 16y squared plus 16. You could combine the 16 and 1 to get 17, so you could have that. So either answer is okay. This next one, you know, when you get into this inverse secant, inverse cosecant, you got this absolute value that pops up. And that'll pop up in this problem. This, first of all, was this should be inverse secant of square root of s, or I could just change this to f of x. So I went ahead and just changed that to square root of s. So we followed the rule. It would be 1 over the square root of s times the square root of s squared minus 1. Then you got to multiply by the derivative of the square root of s. So notice I'm writing that as s to the 1/2. Okay, well, if we square the square root, that gives s. So this denominator under the radical, that's s minus 1. The derivative of s to the 1/2 is 1/2 s to the -1/2. And when I put this together, I just multiplied straight across, so that 2's in the fraction, and then the s to the -1/2. See, I just moved that to the bottom and changed it back to a square root. So that s to the -1/2 just went there. Okay, now you're squaring a square root, even though 1's an absolute value. If you square that, the square root of s squared is going to be positive, since you're doing that in an absolute value. So you could go ahead and do that and then write the answer like that. Either way is okay. You could just leave you can always on these just leave the absolute value if you want to. For now, it's not that important for what we're doing. Okay, I'm putting myself to sleep. All right, that's not good. Okay, so the next thing I want to look at is an example of equation of a tangent line with an inverse trig function. So let's take a look at this then. And we could graph this on a calculator to kind of do a nice check on this too. So, well, we already got the point, so that's nice. We do need to find the derivative to find the slope of the tangent line. So the derivative of an inverse cosine is, it begins with c, so it's negative. -1 over the square root of 1 minus that argument squared. Okay, so that's how you do that. It's the formula is -1 over square root of 1 minus x squared for the inverse cosine. Okay, chain rule, you also got to multiply by the derivative of the function inside, x squared. So we need to do that, get that taken care of. Okay, so let's work this out then. We have -1 over the square root 1 minus x to the fourth times 2x. So I'll just write this derivative as -2x over the square root of 1 minus x to the fourth. Then to find the slope of the tangent line, I need to plug in this x value, which is 1 over square root of 2. So that 1 over square root of 2 is going to plug in for x. So we may have to deal with a little bit of algebra on this. We'll find out. Okay, I'm falling asleep. Okay, putting myself to sleep. That's horrible. All right, so we have -2 times 1 over square root of 2, and then under the radical I have 1 minus 1 over square root of 2 to the fourth power. So yeah, there's some algebra involved in this thing. So first thing that I would recommend that we do, we could go ahead and rationalize this denominator right here. And we could go ahead and get that out of the way, and then I'll kind of at the side of the paper we'll work out that the 1 over root 2 to the fourth. So what I'm going to do is just over the side of the paper, let's just rationalize the denominator. So that would give square root of 2 over square root of 4. So that's square root of 2 over 2. So I'm going to write this in my next step as -2 times square root of 2 over 2. And then in the denominator, I'm going to go ahead and write this as 1 minus square root of 2 over 2 to the 4th power. Okay, so notice that cancels out, so that gives you negative root 2. Okay, now in the denominator, I'll kind of do a little bit of work, some scratch paper here. So if I've got square root of 2 over 2 to the 4th, I'm really just doing the numerator to the 4th, so I'm doing the square root of 2 to the 4th over 2 to the 4th. 2 to the 4th is 16, so I have square root of 16 over 16, which is 4 over 16, which is reduces down to 1/4. So what I'd have is the square root of 1 minus 1/4, like that. Okay, now I'm going to move this over here, and I'm going to continue this here. So what I've got here is I've got negative square root of 2 over, get a common denominator, and that would be 4/4 minus 1/4. So that would be negative square root of 2 over square root of 3 over 4, like that. Well, that would be negative square root of 2 over the square root of 3 over 2. Okay, I want to take this as far as we possibly can and get this simplified, make it as simple as possible. So the square root of 4 is 2, that comes out of the radical. Well, this is a division problem, so this is really negative square root of 2 times 2 over root 3. So that would be negative 2 root 2 over square root of 3. All right? And we can go ahead and rationalize that denominator. That's what I'd recommend we do. So I'm going to multiply by square root of 3 over square root of 3. That'll give me negative 2 root 6 over 3. So that's the slope of my tangent line. Now I'm going to erase this stuff over here that I kind of did on the side. That may be the hardest part of the problem right there, is doing all that arithmetic right there. Okay? And so what I'm going to have here is we've done all that work to find the slope of the tangent line. So now we're going to use the formula y minus y1 equals the slope of the tangent line, x minus x1. This will be kind of a messy answer. So the pi over 3 is the y value. The slope of the tangent line is negative 2 root 6 over 3. And then x minus 1 over square root of 2. I'm going to change that 1 over square root of 2 to square root of 2 over 2 in a rationalized form like that. Okay, then I'm just going to multiply this out. And I'm not going to have to do much simplifying on this. So I've got this basically. I've got y minus pi over 3 is equal to negative 2 root 6 over 3x, and then plus 2 root 12 over 6, like that, and then that can be simplified. It's good algebra exercise to do this. I'm going to move the pi over 3 to the other side, so I get y equals negative 2 root 6 over 3x. And then this part right here, I can break this up into square root of 4 times square root of 3, so that's 2 root 3. So we would have 2 times 2 root 3, and then the plus pi over 3 when we move that over. So a good answer would be y equals negative 2 root 6 over 3x plus 4 root 3 plus pi over 3. Okay, so that would be the answer to the equation of the tangent line. So that's kind of a messy problem, but it's kind of good to work with trig functions and inverse trig functions for the practice of that. And then we could put this on the graphing calculator and check. Okay, I just paused because I think I made a little mistake on here. And this is getting a little messy here. So let me correct myself. It'd be better if I just wrote it more steps. Okay, so I've got y minus pi over 3. Let's see, this was a 6. Okay, equals negative 2 root 6 over 3x. And then I'm going to change this to 2 times the square root of 4 times square root of 3 over 6. I think I forgot about my 6. So I've got y minus pi over 3 equals negative 2 root 6 over 3x. And then this would be 2 times 2 would be 4 root 3 over 6. And that would reduce to 2/3. So what we would get is y equals negative 2 root 6 over 3x plus 2 root 3 over 3 and then moving the pi over 3 to the other side, you would get this. So that would be the answer. I was going to show you on the graphing calculator, so I'm going to pause and get that set up. Okay, so let me show you kind of what goes on the calculator here. So if I put in the function inverse cosine x squared, and I have to put this in like this, and I put that in, and then the window, I think I just did like this, -2 to 2. So here's the idea. You can see that's a tangent line, and if I trace at the x value 1 over square root of 2, that's the point where it's tangential. So that's right. You can look at that on the graphing calculator. All right. Okay, so I just kind of put these graphs over here. This, if you want to see how I put that in, that's how I put it in. That's the window. So you can tell that that's right. Okay, that's kind of a messy problem with arithmetic. All right, down at the bottom of the page, I just have the graphs of the inverse trig functions. Not going to really go over this. These are kind of important things just to refer to from time to time, the domain and range of the inverse trig functions and what their graphs look like. The next page, we're going to just wrap this up with one application problem. And this is kind of a nice application of a... Okay, so this is a nice example right here. So what we have is we have a boat that's sailing towards a 150 millimeter, that isn't much of a skyscraper, skyscraper. And yeah, if you stepped on that skyscraper, you'd crush it. So anyway, the sailboat's going towards the building, and as it moves towards the skyscraper, the angle is getting bigger. Just, realize what would happen. By the time the sailboat's close to shore, that angle's even bigger. So we're going to call that angle theta. The distance from the sailboat to the base of the skyscraper is x. So we have that. So the question A is, what is the rate of change of the angular size, d theta over dx, when the boat is 500 meters from the building? So we actually have two choices on this. We have, if you look at theta and look at this side diagram, that's the side opposite. This is the side adjacent. So remember, the tangent of theta is opposite over adjacent. And if you look at this diagram, that would be 150 over x. We could also look at it with the cotangent of theta, which is just the reciprocal, adjacent over opposite, which is x over 150. Now, you could do this problem either way, but this one's better because the x is in the numerator. So, because I'm going to do the derivative of both sides, and I like that x in the numerator. So what I'm going to do is I'm just going to write this down like this as cotangent of theta is equal to x over 150. Now what I can do on this, you can do this in your head too, but if you do the inverse cotangent of both sides of this equation, which is what I'm going to do. I'm going to solve this equation for theta. So I'm going to be doing the inverse cotangent of both sides. Okay, then what happens is this. You get, if you do the inverse of a function, it undoes the operation. That gives theta. So we end up with theta is the inverse cotangent of x over 150. So that's kind of the first key to the problem is getting that part figured out right there. So what we're going to do is, since we're trying to find the derivative, we're going to do the derivative of both sides of this equation with respect to x as suggested in the problem. So we're going to go ahead and work with our derivative. And we learned the derivative formula for the inverse cotangent, so that'll certainly come in handy. I think I'll write this also like this as 1 over 150x. That means the same thing. Okay, so when we do this derivative, it's going to work like this. This derivative here is just going to be d theta over dx. Okay, so that's all you can do on that side. If you do the derivative of theta, it's 1, but you're doing this with respect to x. So since these variables don't match, you have to write it that way. And then remember, for the derivative of a inverse cotangent, we learned that that is -1 over 1 plus x squared. So we're going to go ahead and put this in. So we have negative 1 over 1 plus, and then that would be 1 over 150x squared, like that. And then we have to do the derivative of the inside part. Now I'm just going to do this in my head because it's easy. The derivative of the inside part would just be 1 over 150, like that. Okay, then what I'm going to do is I'm going to simplify this, as far as I can on that then. So I'll take you through a little bit of the simplification on here. All right, so I'm just going to move this down here. So I've got negative 1 over 1 plus, and you would have to square the 150. So I'm just going to write this as x squared over 150 squared times 1 over 150, like that then. Okay, now I'm going to do a little bit of algebra over here at the side. So I'm going to write this again as negative 1 over 1 plus x to the second over 150 to the second times 1 over 150. So what I'm going to do on this then, see, this can go in the numerator too. So you could do this if you wanted to. You can put the 1 over 150 in the numerator, or it can go through the denominator like that if you want to. So what I'm going to do is I'm going to do this. I'm just going to write this as negative 1 over 150 over 1 plus x squared over 150 squared, like that. And what I'm going to do is I'm going to get rid of this fraction. So if I multiply both the top and bottom by 150 to the second power, that's going to get rid of that fraction for us and make this expression a little bit easier. And just leave the 150 squared alone. Don't use your calculator or anything. So what you'll have is in the numerator, you'll have negative 150 squared over 150. And the denominator, when you distribute, you're going to have 150 squared plus 150 squared x squared over 150 squared. Then you got a cancellation there. And in the numerator, one of those cancels. That'll just leave you negative 150 over 150 squared plus x squared. So this is your derivative right here, okay? So again, a little messy with the algebra on there, but that would be a simplified form of your derivative. So now what we want to do is we want to find d theta over dx. We want that evaluated at x equals, and they say when you're 500 meters away from the building. So we're just going to replace and plug that in. So we're going to have negative 150 over 150 squared plus 500 squared. So I'm going to go ahead and just get my calculator out, and then I'll put that in. Okay, so I'm going to go negative 150 divided by, make sure your denominator's in parentheses, so I'll do 150 squared plus 500 squared. Let's put an extra 0 in there. Okay, like that. And this will be an answer in radians. And that's giving me negative 5.5 times 10 to the negative 4. So that just means move the decimal back 4. So you would have 5.5 with 3 zeros, like that. And then that would be radians per meter. So that would be the rate right there. That would be the answer to the problem. So basically what's happening is at that point of time, when you're 500 meters away, this is the rate at which the angle is changing. And you end up with a negative answer on that. So that would be the idea. Okay, we're also going to look at this graphically and just kind of look at that idea. So that's how you would work that out. Okay, so I went ahead and got everything set up on the graphing calculator. So what you need to do is put in your calculator, put the function in like this. So this is your derivative right here. That's what we're graphing, is this thing right here. And then this is a good window. This would be 0 to 1,000. And then I'm doing very, very small y's on that. So you put that in, if you get everything set up. Okay, there's your derivative that you're graphing. Get your window set up. You'll have a graph like this. And a couple things I wanted to notice on this is basically what happens on this. If you trace at 500, this problem was 500 meters away. Okay, then it gives that same value over here, the negative 5.5 times 10 to the negative 4. So what's happening is the rate is changing on this. So this is the graph of a derivative, not the function. So this is really telling you how the angle is changing as you get closer and closer to that skyscraper. All right, so basically what I want you to do on that is just sort of sketch that out on your calculator, and then you can just put a graph like that just to kind of check that out, and that's a good way to check that you're correct on that. Okay, so that'll wrap this up. Kind of a long section with a lot of information, a lot of technical things, so hopefully this will help you with your inverse functions. Good luck.